We're now going to look at the moving average and moving range charts. And the moving average, or MA, and the moving range MR charts use sample averages and sample ranges just as we did for the regular X bar and R charts. But the method of forming the samples or subgroups is different. So suppose the sample size is n, right? We decide we want to pick a sample size of n. When we start the control chart, the first subgroup is made of the first n number of consecutive measurements. So we start by adding these all up and calculating then an X bar and a range for those first n values. And then when the next value comes in, I can change the color here. When the next value comes in, n plus 1, you calculate the new X bar and range with that new value and getting rid of the old value. So, I mean, mathematically, if you want to write that out, the moving average then for the ith moving average here is going to be the most recent measurement, and then go back until you have a total of n values, n measurements, values. Then you add them together and divide by n to get this moving average. Now, the averaging done in these MA and MR charts reduces the noise. So this is an advantage then over what we've had before. It helps in discovering the signals. Larger subgroup sizes, and so you have to decide on what n you want, they'll tend to smooth out the variations in the individual observations and bring out the signals better. But they may hide changes. They may hide changes that occur during the time that the sample is being taken, because if you're taking more, you're averaging them all together. Smaller subgroups, though, may be more responsive, but they'll be more sensitive to noise that cause maybe excessive fluctuations in the moving averages and ranges. So again, subgroup sizes of 4 and 5 seem to provide a pretty good trade-off in practice. You could also choose your subgroup size to reflect what is actually happening in the process. So for example, if you have a certain number of batches, so you have, for example, batches of chemical and 3 batches are produced from 1 batch of raw material, then it would make sense to have a subgroup size of 3, because as soon as the raw material changes, you would hopefully see that in the moving average and the moving range if you keep your subgroup fairly small to a size of 3. So here we show the control limits again for the moving average and moving range charts. If you have the first 20 observations from a stable process, you can see that these are actually exactly the same values as we had for our X bar and R charts. If we have standards, this T and sigma naught, we know where we're supposed to be running, we can then use slightly different control chart equations. Again, we're not worried so much about you calculating these, but to be aware of them. What we'd like to show you, though, is the example and compare it to the example with the X chart. So don't forget, before we had the first half of the data coming from a process where the mean was at 10 and the sigma was at 1, and then after 20 samples, the mean shifted to 11.5. It shifted by 1.5 sigma, and sigma stayed at 1. So we want to see how the MA and MR control charts which were designed for the original 20 observations, are able to detect the change in the process average when it occurs from the 21st observation. So here's our data again. Now what we can see here, the first 20 observations to get this moving average value. So we take these 3 values and we calculate a moving average, add them together, divide by 3. So here we have n equals 3. And the moving range, well, we have here 10.62 minus 10.09 to get a moving range for those first 3 values equal to 0.53. Now for the next one, you drop off the original value and you take the new value and you come up with a moving average and a moving range for measurements 2 through 4. And you keep going with this. You take off the old value and add the new value and calculate a moving average and moving range. So if we didn't have any standards, we would then use those values, use the overall average of the moving averages and average of the moving ranges to calculate our control limits, because we're interested to see how we will detect the shift. But in this case, we have our T and our sigma naught, so we can calculate then T plus A naught becomes 10 plus, and here we have 1.732 is our A for n equals 3 this time. This is moving average with n equals 3, 1.732 times sigma naught of 1. We get upper control limit of 11.732, lower control limit of 8.268. And likewise for the MR chart, we find that our D2 is going to be 0.4358, and little d2, 1.693, and then d1 is 0. So we end up with upper control limit of 4.358, control center line of 1.693, and lower control limit of 0. So let's look at this. Here is the 11.73, 8.268, and here's our first 20 measurements. Change occurs, next 20 measurements, and we see detection at sample 27. So it's at the 7th measurement, the 7th moving average sample from the change. So you can see here, so this example, this is slightly more, or quite a bit more effective than just our simple X-bar chart, or sorry, X chart for individuals, where the control limits were quite large because we had so much variation in the individual values. So just one note though, we have to be cautious in making general conclusions. This is one example. The added power or result of average from larger subgroups should be expected. And here we show, just for completeness, this was what we just showed you, the moving average chart, and here we have the moving range chart. And here we don't have a change in the sigma, we don't see a difference there. There's no change. Okay, so good, very good. The last is the exponentially weighted moving average chart, or EWMA, and we're not going to go through too many details here. There is more in our textbook. This is widely used, but we're going to just go over a few main points. So we noted that the conventional X-bar chart with n equals 4 or 5 with the 3 sigma limits is not sensitive to the small changes in the process mean, and for example, less than 1.5 sigma magnitude. We also noticed that noted that the sensitivity, we improved sensitivity through 1 and 2 sigma warning limits. That was the idea of the Western Electric rules that we've had before. We could also use those to detect runs or other patterns. So another approach, though, is to use statistics that accumulate information from several past samples. And so that's sort of the idea of the moving average and the moving range as well. There's 2 other methods of doing that, is the EWMA, the exponentially weighted moving average, or the cumulative sum chart, the Q-sum control charts. And researchers have established that these are very effective, or equally effective, in discovering small changes in the process mean, but the EWMA is a little bit easier to understand and to construct, so we're only going to look at that one here. Now, if we have xi as the observation from the ith sample, then what we can do to create an EWMA chart is to calculate a moving average, but a weighted moving average, an exponentially weighted moving average, which I've denoted here by this W, as lambda, so a constant lambda, times that value, plus 1 minus lambda times the previous value, or the previous weighted value in this case. So what we have here is lambda is a smoothing constant, and it's between 0 and 1. So, I mean, if it were 0, that wouldn't really, the first value would drop out. What you want to do is to have a lambda which will weight the most recent values. The larger the lambda is, the larger this value is, the higher the weight you have on the most recent data. And then this will begin, as the larger lambda is, the smaller the weight on all the accumulated data that you've had before. So if you expand this, so here's the lambda xi is here. If you expand this wi minus 1 times 1 minus lambda, you end up seeing that you're going to have lambda times your most recent, lambda times 1 minus lambda from the next most recent, lambda times 1 minus lambda squared times the next most recent. So that the older data, this is the older data, this direction, the weighting becomes smaller and smaller. So you can change lambda as you like then, but you're still getting information from the old data. You're not just, your value that you're reporting is not just simply the value that you're measuring, it's the value that you're measuring plus some a large proportion of the value that you're measuring, plus some smaller proportion of the data before that, and the data before that, and the data before that. So lambda determines the relative importance given the most recent values. And what's the best lambda to choose here? This is a bit difficult because it depends on a lot of specific factors, such as the magnitude of the changes you're looking for, whether the changes are positive and negative, and there's a lot of research still going on in this. But what is useful here is that this EWMA chart can be changed, the sensitivity or power can be changed by changing the value of lambda. So you could take your data, and this is also, there's an example in our book on this one, but you can change the different values of lambda and find the chart with the right amount of power for your needs. And you can't really say that about the other charts, including X bar and R. You can change the sample size, you could change the frequency, for example, but you're not actually changing the calculation used to do the chart. So that's just a quick review of that one, but at least in this section, we've had a good look then at the different types of control charts that you can use for slow-moving data.